Welcome back, ladies and gentlemen. So now we've gotten to our last section that we're going to kind of talk about in our packet. So we've discussed a lot about our first unit, which is the idea of discussing how objects can move at a constant velocity and kind of touching on some of the concepts that we're really going to focus on for the rest of the year. The idea of what the velocity of an object is, what position is, how we can figure out these things by reading graphs, and kind of how we can take the motion of an object and represent it through a bunch of different graphs, drawings, or diagrams. So we've talked about the idea that we can draw a position time graph to map out the motion of an object, a motion map to map out the motion of an object, and we've also talked about this new type of graph, this velocity time graph. All right. Now, what we're going to talk about today, just kind of wrap up this unit, is to kind of focus on how you can use a velocity time graph to figure out kind of the motion of an object. All right. And we're going to also talk about kind of the other way. This is the second way we can kind of look at a graph and kind of get more information out of it besides just reading it. All right. So to do that, you're on the very last page of the packet. All right. I'm going to actually kind of call this worksheet number 5 because it really is kind of unique to this particular topic, and it's not really related to what was talking about in worksheet 4. So this is worksheet number 5. All right. Now, you'll notice that this has been given, we've been given a graph, and it's a velocity time graph for a dune buggy, just like our little buggy that we did our lab with at the very beginning of this unit. All right. So we're given a velocity time graph, and right away this velocity time graph tells us a couple things. All right. So the first thing we want to do is let's just kind of remind ourselves, and honestly, this would be a great warm-up. If you want to pause the video, I want you to write in words what's happening in this setup. All right, so a really good warm-up right now is just literally write down, describe in words the motion of this dune buggy. All right, and make sure you read the directions because they might give you some information that's important that a velocity time graph by itself might not tell you. All right, so take about 3.5, 4 minutes, do your warm-up, and then once you're ready, unpause it, and we'll go from there. All right, so hopefully you had a chance to kind of go through that warm-up. If you go through and kind of write this in words, there's 4 sections of motion here. All right. Now remember, we talked about this from worksheet 3. The one thing a velocity time graph does not tell us that we need to kind of specify beforehand is it doesn't say where an object starts its motion. All right. It doesn't say the starting point. However, in this case, the worksheet actually includes that because it says, in describing the motion of the buggy, that it starts 20 centimeters from the edge of the track. All right. Now we can assume edge of the track means the origin. So if we're going to describe this in words, we probably start by saying this dune buggy, starting 20 centimeters from the edge of the track, moves with a constant positive velocity of 30 meters per second. Because it gives us numbers here, so we can be even more specific, so we can include that velocity. Then we can say that's for section 1. Then the object turns around and moves at a constant negative velocity of a negative 40 meters per second. All right. And remember that negative sign, once again, I'll keep saying it over and over. Negative and positive in this class only mean direction. So just because this is a negative 40 meters per second squared, this object is now actually moving faster in the second section than it was in the first section. Okay, because 40 is greater than 30. Then in section 3, then the object stops for 1.5 seconds. Then the object starts moving at a constant positive velocity of 20 meters per second. And I keep saying the object, I know it's a dune buggy. But right there, just a little warm-up of kind of translating what this graph is telling us into words. All right? Now, what we're going to find out is that actually we can translate this graph into something else as well. So look for part A. It says determine the change in position from 2 to 3.5 seconds. Clearly indicate how the change in position shows up on the velocity graph. Show your work and use units. Okay. So far, the only way we've talked about how we can actually literally determine the change in position is by reading a position time graph. All right. We can literally look at it and it can tell us what's going on. Now, what we're going to find out is that we actually can use a position time graph to create a velocity time graph, as we already talked about. But we can also do the opposite. We can use a velocity time graph to create a position time graph. All right. And how we do that is we use the second way we can analyze a graph. All right. So, and I apologize, keep saying the second way. There's really 3 ways. There's 3 things you can do with a graph. All right, and this is for any particular math you're going to look at. There's really three things you can do with a graph. You can read the graph, you can take the slope of the graph, which we've already talked about. We did that with the position time graph. We talked about the idea that the slope of a position time graph is just equal to the velocity. And if we look at this, I set this up earlier. So I did a little drawing where I had our guy ran into this wall. All right. And I had him move with a velocity of 5 meters per second. All right. Now, if we kind of read the graph and look at it, we can see that if I look at this particular section of motion, his starting position is 0. Final position is 10 meters. And it took him 2 seconds to cover that distance. All right. And if we kind of use some formulas that we've talked about, we know that the velocity of an object is just equal to the change in position over the change in time. Okay. Well, from this little drawing, we know the change in position is 10 meters, positive 10 meters. And we know this took 2 seconds. You can see from 4 to 6 seconds. So the total change in time is 2 seconds. So we get that the velocity of this particular thing should be equal to 5 meters per second. And if we look at the graph, you'll notice that's exactly what's happened. This velocity time graph, it's a nice horizontal line at 5 meters per second. All right. So if I was only given this graph, I could still create this velocity time graph based off of what I know to do with graphs besides reading them. All right. Now, the other thing we can do with a graph is we can actually create a position time graph by reading our velocity time graph. And in order to do that, we have to kind of make use of the other way that we can analyze a graph besides reading it and taking the slope. And in order to do that, what we have to do is we have to kind of think about the idea that graphs are not just things we look at that are just math. They have physical meaning. All right, a graph physically represents something. So what I'm going to do is I'm going to once again write the formula for velocity. So velocity is equal to the change in position over the change in time. Okay, and right there, that's a really good T. That's also the formula for slope. All right, we've taken the idea of rise over run and we've just turned it into something that has physical meaning. All right. The other thing we can actually do with a graph is that we can actually take the area of a section of the graph and it actually will also mean something to us. All right, so let's say I want to find the change in position from 2 to 3.5 seconds. All right, well, if I look at my formula for velocity, and this is going to seem kind of strange at first, but I promise it'll make much more sense in a second. I can actually move some things around in this formula and I can actually calculate the change in position. So I do a little algebra. Remember, if you're not super comfortable with algebra, we're going to do a lot of practice with it, so don't worry. But basically, I would just multiply both sides by the change in time. So it would become that the change in position of the dune buggy is just equal to the velocity times the change in time. Okay. Now, here's where this comes into the graph. If velocity is found by taking the slope of a position time graph, then on a velocity time graph, what I can do is to find the change in position. I'm going to do the velocity this object's moving at times how long it moved at that velocity for. All right. But what I can do is if I look at the graph, you'll notice that the graph axes, one is velocity, one is time, both relate back to this formula. Okay. And what that means is that I can actually imagine this as a little rectangle. Okay. And if I asked you to find the area of a rectangle, so let's just say I just draw this, I take this little part of the graph, and I say, I want you to find the area of that little rectangle right there. All right. Well, the area of a rectangle, remember, is just the length times the width, or the base times height, or whatever, however you want to define it. But it's just going to be this side times this side. All right. And what we do, and this is where physics becomes really useful with the math, is we take that rectangle formula and we give it physical meaning. So instead of talking about the area, we actually mean the change in position. Instead of talking about the height or the length of this one side, it's actually the velocity. And instead of doing the base of this, that base actually represents the change in time. All right. So what all this means, and I'm going to flip to the master sheet, is that we can actually find the change in position from a velocity time graph by finding the area. All right. And that is going to be the third thing we can do in the graph. We're going to be able to either take the slope of the graph to try and find information about what's going on, literally read the graph, or take the area under the curve. All right. Now, I know there's a lot of words on here and there's kind of a lot of information. First off, feel free to pause this at any point if you want to write down the notes, because I know this is a lot of new information. If you're going into calculus, you're going to find out that this area is kind of the precursor to something called an integral. If you're not going into calculus, don't worry. It's still area, and it's something we can easily do. And we'll keep practicing. If you're like, oh gosh, area, it's really crazy. We'll keep practicing it, I promise. All right? So, because of this, we can actually use this graph to figure out all we want to know about the change in position. All right? So, it asks specifically right now, determine the change in position from 2 to 3.5 seconds. All right? Well, there's two ways we can do it. There's the new area method we just brought up that we can kind of just read the graph and kind of try and find the area. We can also use this formula as well to do the same thing. All right? So, I've done the formula first. So, on the left side, I talked about the idea that the change in position is just equal to the velocity the object's moving at times the change in time. All right? Well, if we read the graph, the velocity is negative 40 meters per second, or in this case, excuse me, it's centimeters per second. Make sure you pay attention to your units here. So, I put where the V is, I put negative 40 centimeters per second. The change in time from 2 to 3.5 seconds is 1.5 seconds. So, delta X is going to be negative 40 centimeters per second times 1.5 seconds. So, the change in position from between 2 to 3.5 seconds is negative 60 centimeters. Okay? Now, I know that was a lot of math I just threw at you. What we just basically found out is that from 2 to 3.5 seconds, the object went backwards 60 centimeters. That's all this is saying. All right? Now, if we decide to do the area method, which is an excellent method, it's going to be really useful for this, all we need to do is find the area between the graph, which is going to be this line right here, and the axis. Okay? And this is a very important point, and this is something that can throw people off a lot of times. I'm going to make the line a little bit thicker so we can read it. When you do this, you are only finding the area between the graph and the axis. Okay, so like if I wanted to find the first section, it would be this rectangle right here. Second section, this rectangle right here. Third section, we're going to find out there is no rectangle because it's not moving. Fourth section, this little rectangle right here. Okay, you do not keep going up, because what happens is if you do that, well, there's no limit to how high up you can go. The only limit is really how big the graph paper is. So the border is always the line for the graph and the x-axis, or in this case, the time axis. All right? So we use the area method. This is really nice because it's already got squares, so literally we can just count the squares and figure out the area that way. So we do the area method. We could see that, this has 6 squares. All right? And all we need to do is just figure out the area of 1 square, and we're multiply by 6. You could do that. You could do it that way. You'll notice in the corner I have that the dimension of 1 square is just 20 centimeters by 0.5. All right. So each square represents 10 centimeters. You don't have to necessarily do that. That can be really confusing, and I know we haven't really talked about the area of squares. The other thing you do, just simply, like we talked about earlier, just write down the length of this side. Remember, this side represents negative 40 centimeters per second, because we can see it. So this side is negative 40. This side is 1.5 seconds. If you multiply them together, you get that whole area right there is 60 centimeters. And it's negative because that's negative right there. Okay? So, once again, all we're doing is we're taking the velocity time graph and just using techniques that we've already talked about in our math classes, and we're actually giving them physical meaning. So when we ask you to find the area of shapes, or maybe we find the area of graphs, in physics that actually has a purpose because it means something. In this case, it tells us how far we've actually gone. All right? So, right there, we finished part A. Part B says determine the change in position from 5 to 6 seconds. Okay? Same idea. It wants you to figure out the change in position of this little section right here. All right? Now, once again, you can do it either way. You can do it the way where you use the formula and calculate delta x. You can also do it where you literally find the area of that little rectangle right there. All right? Either way works fine. If we do the area method, we'll see that the length of this side would be 20. The length of this side would be 1. So the total area of that little section would be 20 centimeters. Ooh. All right? And then if you did the same thing, if you calculated it, you would notice right here, you can see the work. But with the velocity in this last little section is 20 centimeters per second. The change in time is 1 second. So delta x is 20 centimeters. All right? So the very last thing I want you to do is now that we know some stuff about these sections, what I want you to do is you're going to literally draw a position time graph using what we know, using the delta x from these sections. Okay? So you're going to actually work backwards this time and draw a position time graph based off of the information you can find in this graph. Okay? Now, the only thing I will say is that when you scale this up, I would suggest going 80, 40, 80, 60, 40, 20, 0. All right? Oh my goodness, I butchered that. So when you're drawing this, just kind of use this as the high point, make this an 80, and I don't know why I'm having such trouble drawing an 8 today. All right, so 80, go from there. So take about the next 4.5, 5 minutes, mess around with this, try and build a graph. Okay, remember to use your rulers where you can. Make sure that you line up the times correctly, and then once you think you got it, unpause the video, and we'll check and see what you got. All right, so hopefully, ladies and gentlemen, you had a chance to kind of create a graph from working backwards. And once again, if you're just going through this worksheet and this video and you're like, this is totally over my head, I'm so confused, I have no idea what's going on, that is totally fine. All right, if you understood exactly what I said perfectly, what I'd probably say is, well, then I don't know why you're in this class, because you clearly know everything already. All right, so the whole point of being in here is to grow our knowledge and to learn stuff. So we're going to run into things we don't understand at first, and that's totally fine, because we will get there, I promise. So with that being said, let's take a look at the graph. So if we're going to create a position time graph from this velocity time graph, right, we are going to kind of work backwards again, and we're going to basically figure out how much we change our position in each section. And just like we've done before, you can divide this into different sections. Then in this case, looking at this graph is basically 4 different sections. So when we draw our other graph, we can look at it the same way. So for the first section, we have to include the starting point. All right, and what's awesome is it tells us, assume a position of 20 centimeters at t equals 0. So we can say the graph starts right here. All right? Then, what we know is we know that if we look at the first section, we want to figure out how far do we go in section 1. All right? Well, if we do the same method we've done before, if I want to figure out the area of this section, I do this side times this side. So this side is 30 centimeters per second. This side is 2 seconds. So we'll see that the total change in position according to this is 60 centimeters. All right. So after 2 seconds, we need to, according to this, we need to increase. We need to go 60 positive centimeters forward. So by that, that means we go from 20 to 80 centimeters. All right. Now the other pieces, we already did the change in the displacement here. All right. Remember, change in position is just called displacement. We already calculated that. We says it goes backwards 60 centimeters. So it actually ends up back where it starts. And make sure the times match up. So now at 3.5 seconds, Our graph now is back at 20 centimeters. Then for another 1.5 seconds, here the velocity is 0, which means it's not moving. So we just have a nice horizontal line here to represent the position not changing. And for the final piece, when we calculated it, we know that it went forward 20 centimeters from our work previously. So we know that this goes from 20 to 40 centimeters. All right? So because of that, we're just seeing this idea, ladies and gentlemen, that we can take this graph that we've just learned about that really is can be kind of useful, but sometimes we're like, I still don't really understand how to read it. We can take something that's kind of a little convoluted and turn it into a position time graph that we could easily recreate if we wanted to. All right? So we're just seeing once again, ladies and gentlemen, this idea that we can take these graphs and using just techniques that we've already talked about in our math classes, we can get a whole bunch of new information just by either taking the slope or in this new thing, taking the area of the graph. All right? And then congratulations for this last piece. You can just scribble through it. We're not going to do the motion map because it's going to look kind of weird. And honestly, I'm not that worried about it at this point. I think we have some pretty good practice. Okay? So, with that being said, ladies and gentlemen, that's kind of the last piece that we're going to use as we start to move through more complex motion. All right? But with that being said, remember, once again, if you have questions, shoot me an email. Come see me during office hours online. Come talk to me during class. All right? Otherwise, have a great rest of the day, and I'll talk to you later.